Okay, then welcome to lecture number 3, now in winter semester 24-25, in Introduction to the Lattice Boltzmann method. And today, still, we are not talking specifically about Lattice Boltzmann, but we are still laying the ground to understand what we are doing with the discretization of the Boltzmann equation that we call the Lattice Boltzmann method. That is, today we are still working with the original, not quite the original Boltzmann equation, but the simplification that we had last time, the BGK equation. And we look into how this is related to what we call fluid dynamics, so the actually the Navier-Stokes equation. Now, today is a very interesting topic, yeah. You have the Boltzmann equation, or a form of the Boltzmann equation, that is the BGK equation, and we derive the Navier-Stokes equation from this. So we make this link. And this is something very important also later to understand how this link is done with the Lattice Boltzmann equation, which is the discretization of the Boltzmann equation. Okay. Getting started. So the thing we are starting with is the BGK equation. And in this I will now skip forces, because we have a lot to do with this. So external forces like gravity, yeah. So they are skipped. We can easily introduce them later, but here we want to keep things as simple as possible. So the BGK equation is a form of the Boltzmann equation. Basically, the left-hand side of the Boltzmann equation, dt of f, so time derivative of the distribution function, then the microscopic velocity into nabla, so this is the advection term of f, and as a collision operator, we have the BGK type, which is the F equilibrium minus F and all of this divided by tau. So this is the BGK equation. And in this, an important question is, of course, what is this tau? And tau, so tau is the time that we need to go back to equilibrium. So we could say this is a time scale for return to equilibrium. So the idea here is, roughly, when particles collide, what happens is they lose their memory. It's a little bit like boxing, yeah? If you get hit very hard, you can lose your memory, yeah? You don't know what happened before. This is even true for particles, yeah. So when they collide, the thing that they remember is the energy that went into the momentum with which all the partners went into the collision, and the energy with which they went into the collision, because this thing is conserved and the number of particles is conserved. And everything else, so the trajectory they came from, yeah, the direction they came from, this is forgotten, and all the correlations, so whatever history happened to them before, this is forgotten. So this is the idea of this. So they forget the memory of the motion before. Collision. Okay, our picture our picture is the following. Yeah, so there is a particle. Okay, say the particle originally came from here, and say this is the black particle, and now there is a green particle. So just saying a different particle comes from here, and this will diverge the trajectory of this black particle, and say here comes a blue particle, and this will then diverge the direction of the black particle again, right? And now this here, this path that we have been moving in between, this we call lambda. Lambda, so, or say the average length of this, because the path that the particle moves between collisions is of course not constant. Yeah, so there will be a statistical mean of this. So this is why we call this mean free path. And we usually call this mean free path and mean between collisions. But usually we don't say between collisions. Yeah, when we just say mean free path. Yeah. So now see that this particle has a velocity c. Say, yeah. So and then this means that the distance that it travels is the velocity c times the time between collisions, yeah? So tau mean free time between punches. I don't know whether they have in boxing something like this, whether a time scale between punching. Yeah, we should compute this. And c is the mean magnitude of particle velocity. Okay, so it's a little bit complicated expression. Actually, it's the mean root mean square, if you will. Yeah, because the mean velocity of the particles is, I mean, in a resting fluid, yeah, is the mean velocity of the particles, of course, 0, right? Yeah, but the magnitude of their velocity is, of course, not 0. Yeah, they are always in motion, but they just these motion cancel out in all directions. So it's like the mean, it's actually the mean square, the root mean square of the velocity. Yeah. So, but this gives us an understanding what this mean free time is. Namely, it's related. Okay, so it's basically related as a now proportional. Yeah, right, proportional like this. When we rearrange this, is lambda divided by cs, because cs is the speed of sound, and this is related to the root mean square, or to the root mean square of the particle velocity. So this tau then becomes potentially up to a constant, yeah, that may also depend on the shape of particles also, yeah. The mean free path divided by the speed of sound. Okay, these are still, well, numbers. Okay, the speed of sound is easy to measure. The mean free path is potentially not so easy to measure, but this can also be done. Maybe I mean, the way it was actually measured is from the theory, yeah. So from so the way it was originally measured is actually the result of when we go through the entire lecture today, yeah. So because they know the Navier-Stokes equation, they had to make this relationship between the Navier-Stokes equation and the kinetic theory, and then they could measure the viscosity, and they could measure the speed of sound, and then from speed of sound and viscosity together you can measure lambda, yeah. I mean, you can calculate lambda, yeah. Otherwise, it's not so easy to measure directly. Okay, but this is the result of what we are looking at today. So now these are very dimensional quantities, and everybody who has studied fluid dynamics to some extent knows that we like dimensionless numbers. And the idea behind dimensionless numbers comes from this Buckingham theorem, or what Buckingham called his theorem, P theorem. Dimensional analysis. Everybody familiar with Buckingham or P theorem? Okay, good. I see some nodding. Yeah, so, okay. We don't go into the detail of this, just recognizing natural systems. Can be described by non-dimensional numbers. By the way, which do we have Buckingham theorem somewhere in our lectures, or did you learn this somewhere else? Both. But we have, where do we learn Buckingham theory in? In fluid mechanics. Okay, yeah, fluid mechanics. That makes of course sense. With all this rank thing included.
Do you mean
the matrix where you actually compute the rank?
Yes,
Yeah.
yes.
Okay. Good. Okay. So we don't need to spend time of this, because this is potentially well known, but we'll see whether fluid dynamics uses all the quantities that we are using here. So of course, if we quantities. Okay, so obviously the world is dimensional, so things that are interesting for us is the velocity. Velocity scale. I mean, this for dimensional analysis, you're not using any specific velocity, but the state of the system, but you have a state, you have a scale to which you compare the state of the system, yeah? So say we have our wind channel, yeah, and it's supposed to be a car like this or whatever, and now we can say, okay, we have a velocity u and we have a length l, and for example the car does not necessarily need to move with 1 meter per second, yeah, it's just we compare to a scale of 1 meter per second, yeah, and then there is a length, yeah, that natural, stop writing. There's the system. Okay, I should not always right from my script. I should actually, but yeah, this is one, for example, 1 meter. Yeah. Okay. So these are dimensional numbers, and the other dimensional number that is usually not included in fluid dynamics is the mean free path. Yeah. So in fluid dynamics, we would look at velocity and length scale, but the mean free path will not usually be considered in the usual fluid dynamics. So this leads to the condition where we have potentially, I mean, they will do something other, but in the end equivalent, they will include the viscosity. Yeah, but including viscosity and mean free path are equivalent physically. Yeah, so they use other numbers. So we have Knudsen number. In your fluid dynamics class, did they talk about Knudsen number?
I don't remember.
Because I guess not. I believe they did not. They did not. So this is something that comes from kinetic theory. Yeah, Knudsen number. So the Knudsen number is the mean free path divided by the system length. And then there is something that the fluid dynamics guys are of course using all the time. Is the Mach number, is the velocity divided by the speed of sound. And by looking at this and by remembering that the speed of sound is the square root of the temperature is the square root of the speed of sound. Yeah, so there's a relation between speed of sound and temperature, meaning that the speed of sound is not constant, means that the Mach number is not a measure of velocity. Yeah, so if how fast is the plane? Mach number is not a measure of velocity. You can misuse it as a measure of velocity because the temperature outside an airplane is relatively constant, and therefore the speed of sound is relatively constant, and therefore you can, do as if this was a measure of velocity, but it is not. Okay, so these are now our dimensionless numbers we are using, and from them we can determine, we can rearrange this. This lambda is the Knudsen number times L, and the speed of sound is the velocity divided by the Mach number. So why are we doing this? Because we know tau is proportional to lambda by Cs, right? So now we plug lambda and Cs in this, and now we see that we get Knudsen number times Mach number times our two scales. So the mean free time is related to the size of the system divided by the velocity, and this times the Knudsen number and times the Mach number. So this here gives us somehow the description of the of our problem, and this will play a role later. So which dimensionless number do you miss here, by the way? Probably the Reynolds number, yeah. So it's somewhere hidden here. You can always rearrange. Things with dimensionless numbers. Yeah, you can. So the Reynolds number is already on the page, but you may not see it in this. You may not see it right now. Okay, but we'll come to it. So now we are looking at some limiting cases that lead us to the Navier-Stokes equation. I mean, limiting cases. Now, we have not yet made any assumption, for example, that particles are close to each other, or that we are in a dense fluid or something like this, or that the Mach number is small. Yeah. So in principle, we have the entire physics. Okay, say Newtonian physics still in there. So what apparently we cannot deal with particles close to the speed of light. Yeah. So because this is not in that particular description, but otherwise we have kept everything inside. Yeah. So going from vacuum to in very high temperatures and so on. And we know that the continuum theory is not applicable to all of this. And this is what we want to derive. So the Boltzmann equation, of course, contains much more information that then we want to use for doing just fluid dynamics. Yeah? So the fluid dynamics is richer. So in order to get to the fluid dynamics, we have to make some limiting assumptions. And these are in particular two, namely we go into continuum. So, okay, in order to go into continuum, or put it the other way around. So when particles are flying through empty space between collisions, yeah, so this is obviously not continuum. Yeah? So there's some disruption. We know that this happens down there, but if we want to consider things in a continuum fashion, we have to assume that this happens on a scale that is much smaller than the scale we are interested in. Yeah? Yeah, and this directly means that the scale we are interested in, the system scale, L, this needs to be much larger than lambda. And if this is the case, then by the definition of the Knudsen number has to go to 0. So, and the second thing we are going to assume is that the flow is slow. This is something not completely required now, but we want to get done with our lecture today. So, yeah, we'll make this assumption too. So U must be much smaller than the speed of sound, and then the Mach number is going to 0 too. By the way, you still have fluid dynamics when the Mach number is not going to 0. So the only important assumption is the first one. The second one is just now for our convenience, because we've already used up half an hour of the lecture. Yeah. Okay. Now this will lead us to the incompressible continuum limit. Limit of the BGK equation. What was this? What just happened? Okay, so and in this we are using some analysis with our moments that we have already introduced. Yeah, so you remember last time we introduced this raw countable moments. By the way, when you search this in the books, I'm not sure they express it this way. That this is raw countable moments is a term that I coined. But it's usually you'll find this other places, but probably not in the book. Okay, let's get to this equation again. Just writing it down. Equilibrium minus the incoming distribution, and now we have to make sure that we understand everything in this equation correctly. Yeah. So in particular, this directional gradient term, yeah, where we have the microscopic velocity and we write the microscopic velocity in, if I write it beautifully, in its components xi, in its components upsilon. I think this is a ugly upsilon, but anyway, this is where I will write it, and this is a zeta. So these are the three components of microscopic velocity, and they go into these partial derivatives in space, dx, dy, and dz. Yeah. So, and this means we can explicitly write this thing like this. There's a dt f plus xi dx f plus upsilon dy f plus zeta dz f, and I take the right hand side now to the left hand side, such that I can write this as all of this being equal to 0. Okay? So now this is the equation. That's the equation we are trying to analyze. And the countable moments, as a reminder, or the countable raw moments, MABC, so it's the integral from infinity, minus infinity to infinity over the distribution xi by the power of a, upsilon by the power of b, and zeta by the power of c. So I have to apologize that, I mean, we used c as a velocity scale before. Yeah, I have to apologize that there are so many things we have to keep track of that I'm running out of letters, unfortunately. Yeah, but this is now just the index here. Okay, so this is the way we compute moments of this f. Now, the thing that is important to grasp now is that we cannot only compute moments of f, but we can also compute moments of the entire equation. Yeah, so the equation that we have up here, we can take the integral, the same integral, and compute moments of this equation. So on the other side, so that I put everything on one side, yeah, is probably not important, but you know, if you integrate anything over 0, it will always be 0. Yeah. So that means, so we get the moments of the BGK equation. And those of you who are thinking, why are we studying here kinetic theory? Everything that we learn here today can be done directly also for the discretized Lattice Boltzmann equation. Yeah. So we look now at physics, and later we look at numerics, and it works exactly the same, okay? So, the moments of the entire equation. Xi by the power of A, epsilon by the power of B, zeta by the power of C, and now comes the entire equation instead of this f. So this is dtf plus dx. Okay, it doesn't because it's linear. It doesn't matter whether the xi is in front or inside the derivative. Yeah, dy now epsilon f plus dz zeta f minus f equilibrium minus f divided by tau. This entire thing integrated over the vector xi, and if you integrate, as I just said, over 0, we'll get 0 everywhere. Okay. Now, what is important to see here is that this xi, epsilon, and theta, they are what we call independent variables. Velocity is an independent variable in kinetic theory. Yeah? So this is opposite to what we have in the continuum theory. Yeah? So being independent means they do not depend on x, y, z, and t. But x, y, z, and t are the things we take derivatives of, right? So we take the derivative of x. So for example, I now, up here I wrote, I put this in front, and now I put this inside. Does this make any difference? It doesn't make any difference, yeah, because xi is an independent variable, yeah, so it does not depend on x, yeah, and the same thing for all the other derivatives, yeah. So we can, which means we can take these guys here up front and put them also inside all of these, yeah. So we can use the distribution law, yeah, and put all of them here inside, and have the same equation. And I'll go to, because this will be our master equation, we call this equation 3.1. So when we do this integral, so we put, so basically what we can do, we can put we can distribute all of this here inside, and then we can actually put the derivative outside, yeah? Because they do not interact with each other. We can put the derivative outside. And then what we'll have the time derivative over this integral with this kernel over f, and this is the moment, right? So this means that we get here the moment. So here's no other f in no other microscopic velocity involved. So we get the time derivative of the moment mabc, because xi by the power of a, epsilon by the power of b, and zeta by the power of c times f integrated is this moment, right? So, and then what happens next here? If we put all these guys into this, what will happen is that we have epsilon by the power of b, zeta by the power of c, but here is already xi, yeah? So this means we will have xi plus 1, yeah? So we'll have the the space derivative dx m a plus 1 b c, okay? And then all of this happens for the other guys too, yeah? So for the one in epsilon, what is it called, y, we have this upsilon. So we have MA B plus 1 C, and lastly we have D set MA B C plus 1, and then we only have this this thing here left where we have no other microscopic velocities in front, so this will just become M ABC equilibrium minus M ABC, and all of this divided by tau, and the other side is still being 0. Okay? Now we can, with these countable moments, we can simply write down this equation. Yeah? And now we have not yet specified A, B, and C. Yeah? So we can put their values, and we get, and the corresponding equation just drops out of this equation here. And this is what we call a moment chain. Okay, so we need another paper. So kinetic theory and also Lattice Boltzmann methods works on so-called moment chains. So we can, because we have, okay, why is it a moment chain? If we want to write an equation, a time update equation for a moment MABC, what we need is spatial derivatives of moments that are one order higher. Yeah? So this is MABC, and this depends on other moments. Okay, so for example, let's look at the moment chain. Say we say A is equal to 0, B is equal to 0, and C is equal to 0. So then we are talking about the moment M000, and we know this moment M000 is xi by the power of 0, upsilon by the power of 0, zeta by the power of 0, which is all 1, and this integrated with f over the velocity space, and this is something that we'll then call rho, and this is the density, where it's the particle density, because we have not included mass in the definition of the moment. I mean the mass of one particle. So it's basically the numbers of particles that you will find. Okay. So, and now if we take this into equation 3.1, is we'll have dt. I mean, it's very simple. We just substitute A, B, and C for 0, 0, 0. Then we get M000 plus dxM100 plus dym010 plus dzm000. And now I put the right-hand side to the right-hand side again. Yeah, so put this collision operator, BGK collision operator on the other side. We will have M00 equilibrium minus M00, and we divide this by tau. Now, in order to understand this equation, we also have to specify what is M100. I think we've done this last time, right? So M100 is the integral over from minus infinity to infinity f. So there's just xi, so not the vector xi, but the scalar xi by the power of 1, and this integrated over the vector xi, and will end up here with rho times ux. And equivalently, we'll have M01, 010 is then rho uy, and M001 is rho U Z. Anybody, did I lose anybody with this? No, okay.
No.
So, now we just said that M000 is rho, and rho is the density of particles, and this is a conserved quantity. Okay? When it's conserved, then collision doesn't do anything, right? And this means that the equilibrium, the collision doesn't do anything if the equilibrium equals the state itself, right? M00 equilibrium is equal to M000. This, of course, means that this collision operator now, which I put back on the right-hand side, will disappear, yeah, because it's the same thing minus the same thing. So I can now put everything in a usual format. So dt rho, so the time derivative of rho, I just substituting the moments by their physical meaning, is dx plus dx rho ux plus dy rho uy plus dz rho uz. And as I said, the collision operator is 0. So now I can, so I have a dx on ux, dy on uy, dz on uz. So I can write this in a more compact way by saying that this is dt rho plus the divergence of rho times u is equal to 0. Okay? Familiar to anybody? So this is the continuity equation. So this is true, this thing is true whether it's compressible or incompressible. Yeah? So in an incompressibility means that rho is not only conserved, but it's also constant in time. Yeah? And then when it's constant in time, then you will see that that the time derivative will disappear and you just have the divergence of u being 0. But this is not something that we can see from just looking at this equation. Yeah? Yes. So, okay. So, now this was the first part of the moment chain, but what happens if we go to other values? So, for example, we put A equal to 1, B equal to 0, and C equal to 0. Then we plug this again in our equation 3.1 and just substitute the numbers. Then we'll have M100 plus dx M200 plus dy m. So what index? What index comes?
110. 110.
110, right. So plus dz m what?
101.
101, right. Okay, and on the other side we have M100 equilibrium minus M100. You see, I'm really amazed that I had to fight with all the other guys in this community for more than 10 years to get them accept that you should use countable moments. Yeah? Because if you give names to all of these things, yeah, then this is very, very confusing how this is going on. And you just heard it 5 minutes ago and you can immediately do it. Yeah? So difference. Okay, yeah, use countable moments. They will not be in the papers. In most of the papers. So in the last 10 years, more and more people are using this kind of notation. Okay, so this M100 is rho ux, even though there is no mass in this, we are assuming the particles all have the same mass, and then rho ux would be the momentum, yeah? And the momentum is conserved during collision. So momentum is conserved, which means that the equilibrium, again, is the same thing as what is coming in, and therefore this thing here is equal to 0 again. Okay, so this simplifies stuff. But anyway, we are running into a problem, and the problem is related to, the moment chain. Because you see, we are now writing an equation for this m for basically what is the velocity or the momentum in x direction, and this depends on the second order moments, right? So this is why it's a chain, because now we have to ask the question, what is m200? Yeah, so okay, how can we do it? Very simple. We set a equal to 2, b equal to 0, and c equal to 0, and then we get an equation for this guy that we are missing. Yeah, and this way basically is dt m200 plus dx. Yeah, now you've learned it already. m300 plus dy m21 plus dz m201 being equal to m200 equilibrium minus m200 divided by tau. So
somehow that means that every time you go one up, you have to get
the next one
to the lower,
the higher.
but you get the higher and you want to place it in the lower, right?
Yes, you want right. You in order to get the lower, you need the higher. Yeah, every time.
Is there a maximum for
Do you believe in God?
I don't know.
Okay. No. Okay, we'll come to this. We'll come to this. Okay, M200. M200 is not conserved. Yeah. So far we could always say, so it's conserved. This collision operator drops out, but this guy is not conserved. This guy is not conserved. I mean, why is it not conserved? You think this is related to the energy, right? But the energy is not actually the thing. The thing, and that's the energy, is M200 plus M02 plus M002. This would be the energy, and this would be conserved. So that the sum of the three is conserved does not mean that the thing itself is conserved. Okay, so now we are a bit in trouble. So up there in our previous equation, what we had is this M200. Now, what can we do? We can use this. I mean, here we have the time derivative of M200, which we don't know, but quite interestingly, because this is not conserved, so this does not vanish. Yeah, we also have M200 by itself because it is not conserved, right? So because it is not conserved, we can write that this is M200 is equal to, so we'll just rearrange M200 equilibrium minus tau dt m200 plus dx m300 plus dy m210 plus dz m201, right? So, and if we, okay, you remember these guys up there. I'm not completely sure, so whether this is on the screen. This and this. So we have to get the three different moments, right? M200, M110, and M101. These are the guys that we need. So we can write the other equations in the same way. Yeah, and because this is so simple now, this is just a structure, you can do this, you can just do this by equivalence. Yeah, so we need M110. So you look at the above equation, it's of course then M110 equilibrium minus tau, and here comes the equation for it from the countable moments. So it's again the time derivative of M110, then here comes dx, and this obviously we are now counting the x component 1 up. This is obviously M21 plus dy M120 plus dz M111, right? So this is, everybody got this already, right? And then the we need M101. This is M101 equilibrium minus tau dt M101 plus dx. Now we are counting x1 up. This is M210 plus dy. Y1 up is M111 plus dz is plus dz M102. Okay, so this is how it always works. Okay, now there are two things. Obviously, there's this ugly equation in the back of this right-hand side, but there's also the equilibrium of these moments. So let's try to stick with what we can immediately solve, and this is the equilibria. Maybe it's a little bit tricky to actually solve this. We know the equations and we can do it. I do it this way, that I plug it into Mathematica and just give me the result. So we know the distribution function, and we have not derived this in detail, because we are not in a physics course actually. Yeah, so we'll have this prefactor here. We know this is a Gaussian function minus vector c minus velocity. So this is the macroscopic velocity. All of this squared. Then there is particle mass m, Boltzmann constant t, and in order to get the second moment, we multiply by xc square and integrate over vector xc. And I put this into Mathematica and get rho Boltzmann temperature times temperature divided by mass plus ux square rho. The same thing have been done for this moment here. As always, a lot to write. Okay, Boltzmann divided by particle mass, temperature, all of this to the power of 3/3 times e by the power of vector velocity minus macroscopic velocity, all of this squared, particle mass divided by 2 times Boltzmann constant times temperature. Now we integrate once in x, so this is xi, that's a more beautiful xi, times 1 in y, once in y, this is 1 epsilon, and all of this integrated over xi, and the outcome of this is rho u x u y. And okay, do I squeeze this in here? I will going to squeeze this in. The 101 is the integral over rho divided by 2 pi. You know, the 2 pi actually comes from that we integrate over a sphere in. Yeah, this is why we get this pi in this. Minus u square m divided by 2k Boltzmann t, and here we multiply with xi and zeta, and then we integrate this over xi, and you can guess the outcome, it's u x u z, okay? So, let's continue again with the question with which we actually started. Oh God, we have only 1/2 hour left. Okay, but we'll get to it. We manage. So we started more or less with the question: what is tau? Yeah, and we've given the answer that tau is equal to the Mach number times the Knudsen number times L divided by U. Okay, now let us assume that the system is very large. Are you, it's the same as before, you checked?
No, I just wanted
Okay,
to see
no.
all the
Yeah.
summary, but yes.
Maybe sometimes, you know, I heard that people looking at my lectures online, they said it's pretty chaotic but quite good. And so I'm potentially making a lot of mistakes here. So watch out, yeah. So okay, I said. Okay, then I said quite good about my own lecture was, of course, completely out of but I was just. So these people who think that my lectures are good still think that they are very chaotic. Okay, so there may be mistakes all over the place. Yeah. So assume the system is very large. When the system is very large, then the mean free path compared to the size of the system is very small, and then Knudsen number is going to 0. And because the Knudsen number is in there, we could now assume, yeah, for the analysis here, that the tau is going to 0. So if tau is going to 0, more or less we are doing this because this helps us a lot. Yeah, why is it helping us a lot? If I may just go back here, because the tau is in front of the thing that we don't know, right? And everything else we know. Yeah, so if we can set tau to 0, we can deal only with stuff that we know. And then the stuff that we know looks like this. The time derivative of m100 plus dx m200 equilibrium plus dy m110 equilibrium plus dz m101 equilibrium is equal to 0. Okay, so now we know all of this. So let us plug it in. dt rho ux plus dx rho Boltzmann constant times temperature divided by particle mass plus ux squared times rho plus dy ux uy rho plus dz ux uz rho, all of this equal to 0. Okay, so this is already the equation. In order to understand the equation, we just rearrange it a little bit. So let's see, we now have rho and say a little bit more beautiful writing, please. Okay, so we have a time derivative of rho times ux. Yeah, so of course we have to apply the chain rule to these things. Yeah, and what I'm going to do is, so what is interesting is that ux appears in many places here, right? So when I apply the chain rule, I'll always put the ux in front once. So, and let me do this first. So the first term here, so the time derivative, I have ux dt rho, and I'm now not going to write the other part, yeah, but I'm plugging out everything where I can put ux in front, and I leave the rest for later. Yeah. So I go on with this guy here. We have ux dx rho ux, and somebody is already probably crying out, no, this is twice this, but we'll see the other part later. Yes, so then I go on with this here. Then we have ux dy uy and rho, and of course ux d. Okay, I should always write it in the same order. Z rho u z. Okay. So now I've taken all of this where I can pull out the ux. Yeah, so this means, of course, there are things missing. I use a different bracket now. So the other thing would be rho dt ux plus, now I've always have to pull the other thing out. So because I had pulled out ux, now I have to pull out rho ux. Yeah, dx ux plus rho uy dy ux plus rho uz dz ux. Okay, I should, sorry for using the wrong bracket. And what I'm now going to do is I'm still missing this part where no ux was in it, right? And I'm going to put this on the other side of the equation, where we previously had a 0. So I write that this is equal to minus now dx rho Boltzmann constant by mass times temperature. Okay, I'm writing this way because this is now close. We want to get closer and closer to how the equation later looks like in the textbook. Yeah. So first thing to recognize is that everything that I put in this, this kind of bracket here. So this kind of brackets I can rewrite as ux dt rho plus divergence of rho u. Okay? And you remember from what we just saw that this thing here is 0. So the entire thing here is 0. Yeah? So we can forget everything in this bracket. And this is not assuming incompressibility. Yeah, this is true. Not even if the flow is not incompressible. So the rest that we have has rho everywhere in front, so we can write rho outside, rho dt ux, and now we can put everything else here together as rho vector u scalar product on nabla ux, yeah, because we have always the derivative of ux, and this is equal to minus dx rho Boltzmann constant by mass T. So, does this already look familiar, this equation? It's the momentum equation, but what kind of momentum equation is it? So there's a few things that are still looking strange. For example, this here. Yeah? So here, I'm always confused, is this the right English term is ideal gas or perfect gas? I don't know. Perfect gas law, ideal. Okay, in Germany we say ideal gas. You say ideal gas, so ideal gas is P times the pressure times the volume is Boltzmann constant times T. Yeah. So and our volume, because we have the volume is okay, because rho is the particle density. It's the number of particles. It's not the mass. So this is why we just have this volume here, and then we can write that P is equal to rho Boltzmann constant times T. Okay, and the mass of a particle is just a constant here. Yeah, so this is how heavy a particle is. So you see, what we have on the right-hand side is the pressure. We have the derivative of the pressure. Yeah. So and now this gives us rho dt ux plus rho velocity into a scalar product into nabla ux equals to minus 1. I mean, it's a constant, so you can put it in front, 1 over m, and the x derivative in p. And now this is now a scalar equation, but you can of course do the same thing for the y direction and the z direction again, and you can imagine it will look exactly the same, and then this is a familiar equation. It's the Euler equation. Now we have to write the Euler equation from this. Okay, big question is, yeah.
I just have a question, because what the assumption here was that the system is very large, and
Yeah.
then the relaxation time approaches to 0.
Yes.
But the relaxation time can't be 0, right?
The relaxation time can be 0. Okay, good. You see, this is the next sentence on my script here, in my notes. Okay, so you are concerned that the relaxation time cannot be 0. Can also not be negative. This is something that we learned from the ESA theorem. So tau is larger than 0 in reality. So what to do about this? If it is not 0, then everything that we had before with the tau in front now enters our equation. Yeah? So let's write the equation again. So we have on the left, we have rho dux plus rho u times dx, and this is equal to minus 1 over m dxp. Okay, so this is what we had before. And after this, we said tau is equal to 0, and we dropped all the other guys. Now we still have the other guys. So what I'm now going to, I need, if you write this down, you need to write it down in a similar fashion than me, because I'm now, this is a lot of stuff, and I'm writing them below each other, yeah? So, if you go back up, you notice that there was these 3 different moments. M200, M110, and M101, yeah? And all of them appear in this format. Okay, or say, right, so for all of them, the M200, it has a derivative of x in front of it, and then comes all this non-equilibrium stuff, yeah, that we identified before, dt m200 plus dx m300 plus dy, okay, it's not going to, I have a little space here, I'm just so managing, d set m201. Okay, I'm closing this bracket here. Do you follow me, by the way? Because this is something that that maybe we'll have to turn the page a little bit back at this moment and remind us of these guys here, yeah? These guys up here. And we notice we have to, in the momentum equation, we have to take the x derivative of m200. And we have taken out only the x derivative of m200 equilibrium. Now we have to take again the x derivative of all of the rest, and then the y derivative of all of this, and the z derivative of all of this. Yeah? So this is what we are now doing. Yeah? So, but it's important to understand this. I need a little bit more space, so I begin a little bit further up here. So there's the same tau, d set, not d set, dy, and now comes the y component. Now the y component, this is, this was 1, 0 plus dx m 210 plus dy m 120 plus d set m111. I'm not writing any nonsense, do I? No, I don't. Plus tau d set. Now comes the guy with m110 plus dx m210 plus dy m111 plus d set m102. Yeah, so you see, countability, yeah, makes it easy to write these things down. Okay, all of this. Now we are wanting to. So this is the thing that distinguishes the Euler equation from the Navier-Stokes equation. Yeah. So this, all of this, we kind of now call S. And now comes the dirty answer to the question whether this is going on, and the problem is it does. By the way, there are two versions of this, and see, there's in natural laws there is conservation of complexity. Yeah. So in the Navier-Stokes equation, there's something that is called the closure problem of turbulence. And this is something that you see if you want to write down an equation for the turbulence. So you run into the problem that in order, because you're doing statistics on vortices, yeah, so you need higher statistics to define the lower statistics. And the root of all of this is already in the kinetic theory, yeah? Because we are also doing statistics, we have statistical moments, and we have exactly the same problem as the Navier-Stokes equation has, just it does not start with turbulence, we have it from the start onwards. And this is, yeah, the closure problem. So, what is this? We need the next order of moments. So the next order of moments, we know how they look like because we have countable moments. We can do this very easily, right? M300, this appears up here somewhere, is of course M300 equilibrium minus tau, and then we do dt M300, and then we just do the counting, dx M400 plus dy M310 plus dz M301. Yeah, all of this is required. M210 is M210 equilibrium minus tau dt M210 plus dx M310 plus dy M220 plus dz M211 M111 M211 is your homework. Okay? So dot, 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 I wrote dot, dot, dot up there. We need the next order of moments. So what's the problem? Here we need, again, the next order of moments.
M211. M211 or M111?
Yeah, so all of them.
Okay.
I mean, M2, no, what M2, no, you don't need, okay, so the next one would be M201. Yeah, but this is, I mean, this basically looks the same as this one, yeah? We have M, you can just exchange the indices, yeah? So for which we need the next order of moments. So we are ordering always more moments. So we have an infinite hierarchy. So, do we get stuck? How to stop this? Okay, so the next idea to stop this is the following. Let's have an idea. So, I mean, we said previously that tau is small, and by saying it is small, we said, okay, then it's probably 0. But let's say it's probably not 0, but it's still small. Okay? So it's small, but not 0. So our best guess, tau smaller is larger than 0, but our next best guess is to say that tau square is 0. Yeah, that's our next best guess. And then we compute these new moments, M300. M300 is M300 equilibrium plus something of order tau. Yeah? So because it's the equilibrium plus tau once more. And this is then, so the equilibrium is again this ugly equation, this ugly integral, 2 pi Boltzmann constant temperature divided by particle mass by the power of 3 over 2 e by the power of xi vector minus macroscopic velocity squared times particle mass 2 times Boltzmann constant times temperature, and this integrated over this scalar xi by the power of 3 integrated over the vector xi, and this goes with, and then there's this rest term of order tau. And if you do the integral, you'll end up with rho ux 3 times Boltzmann constant times temperature divided by m plus ux square plus o order tau. So, and you can do the similar things. We're running a little bit low in time, but we'll manage. M210 equilibrium. Now you do the integral and you will end up with u y rho Boltzmann constant times temperature divided by m plus ux square. Also, okay, because I now wrote that this is just the equilibrium, of course the M200, okay, well let's, okay, I rewrite it a little bit without equilibrium, and when it's without equilibrium, this is equilibrium plus order tau, right? And then M111, also without equilibrium, is rho u x u y u z plus, because the non-equilibrium part is included, it's of order tau. Okay, now unfortunately, if you want to derive everything completely correctly, now it's getting to be a little bit complicated. So because we have only a few minutes left, we have a few simplifying assumptions that are not actually necessary in order to get the right result, but that will get us the right result a little bit quicker. So that we plug in some assumptions that just simplify our life. So one assumption is that we forget about temperature. Temperature is a constant. The second thing is that we assume low velocity. And low velocity means we said that ux to the third power is equal to 0. Ux times uy square is 0, and ux uy uz is equal to 0. So in particular, these assumptions are not necessary, but in order to see out of the equation that all of them drop out requires really a lot of calculations. Yeah? So we'll just assume that they drop out. Okay, and now we look at what we previously defined as this reminder S. Yeah? So S is equal to tau dx. Now we plug in what we have, dt, okay, Boltzmann t divided by m rho plus dx 3ux Boltzmann t divided by m times rho plus dy uy Boltzmann constant temperature m. So you remember we made the temperature a constant, so now everything in this is of course a constant. Boltzmann T divided by m, plus there is something of order tau in this. Yeah, and you see there is in front of all of this is a tau, and back here is a tau, so the rest of this will be tau square, right? And then we'll assume that this drops out. Plus tau dy dx. So, okay, so in the second part, the time derivative, yeah, because we assume that these velocities here, that the square of the velocity is already 0, it's already dropped out. So there is no time derivative anymore. As I said, this is not necessary. You can plug this in. It's really a good exercise to do this, to see after long calculations that it will automatically drop out. So there's only the two of them left. Also, the derivative in z is also disappearing. Okay, the reason why this is not disappearing is because in M211 we have uy times a constant. Yeah, and now we also have uy times this, and this is third order. This will disappear. Yeah. So this is now shortened to this here, and then there is the third part that is tau dz dx uz Boltzmann constant temperature rho divided by m plus dz ux Boltzmann T divided by m and rho plus O tau. Okay, I'm going to call this bracket up here, I'm going to call this Sx, because we take derivative in x. Going to call this here as y, and this here I'm going to call as z. Okay, now we will simplify this Sx thing by introducing the continuity equation. We put this in Sx. So, see, we can use, so we take dx k Boltzmann T divided by m. So we'll have dt of rho plus the divergence of rho u. And this is equal to 0. Yeah. So if we compare this to the Sx, we see that this is almost the same. Yeah. However, in front of the dx we have 3 times ux. So what is going to remain is that Sx can be written as tau. So now with the second derivative in x, yeah, we have this one plus and this one, dxx, I'm writing it this way. And now 2 of them remain, k Boltzmann T, rho divided by m, and this goes plus tau square, which we're going to ignore.
So what we're doing here is writing the 3 is coming from the derivative of a square term.
No, the 3 is not coming from the derivative. The 3 is coming from the integral up here.
Or, sorry, what we're doing here is rewriting. So we want to get rid of the 3.
No, we don't want to get, no, we don't want to get rid of the 3. No, we want to get rid of, we actually want to get rid of everything.
Okay.
but we don't get rid of everything.
Okay.
So we see there's something that looks very similar to the divergence. Yeah. However, there is here there is in front of the ux we have a 3. So we pull 2 of them out.
Okay.
Yeah. When we pull 2 of them out, we are left with here the divergence, and we know when we add to the divergence the time derivative of rho, then we get 0.
Yes.
Yeah, so this is mostly 0 just up to this ux.
Mm-hmm.
Yeah. So okay, if now we can since we simplified this, now we can rearrange everything according to the derivatives that we have here in front. Yeah, so I keep this up here and rewrite S again. I take tau. So everything in here now has K Boltzmann T divided by M in front. So I'm pulling this out. So our Sx part has a dxx ux rho. Now actually it has 2, but I'm taking out now only 1 in the way I'm rewriting this. And now I notice that there is a dy and a dy here, and there's a dz and a dz here, right? And because I want to arrange my writing like this, that I write dyy ux rho. So this is this thing here, and I want to add this thing here, such that I have this, that I have these terms all together. Yeah. So and now I have to write the rest of them. They have a tau in front, mk Boltzmann t m. So because I pulled out only one of them, I have to leave the other one again. And now I have to write all of the other missing parts. So this is dxy uy rho plus dx z rho. And you see there is a divergence in this again. I write, so the rest of this is of order tau square.
Which would be the missing, the third one, right?
No, these are the third moments. Well, what do you mean the third one?
No, what I'm, because we have a 3, and you split.
Okay, now I split 1. You are talking about this 3 here,
Yes.
right? So we use 1, yeah, in order to cancel with the divergence, yeah, and then we split it again and put it once here and once there.
Yes.
Okay.
Okay.
So and then we can rewrite this S again as tau K Boltzmann T. I'm taking overtime again, sorry. So now this here is the Laplace operator, obviously. So I can of u times rho. And the rest is, there's a divergence, so there's everything in x and the divergence again. So we can write tau K Boltzmann T divided by M dx. And here we'll have the divergence of u times rho again. Okay? So now we can plug this into our equation here, dt rho dt ux plus rho u. So the scalar product on, so this is the advection term in the Navier-Stokes equation minus 1 over m dxp, so this is the pressure gradient, plus tau K Boltzmann t divided by m, and this goes into the second derivative, so the Laplace operator of u times rho. So if we made the calculation more stringent, we could actually identify that we can plug rho in front of this, but we have not, yeah, so this is why I'm keeping it here. Plus dx, the divergence of u, which will vanish in the case of incompressibility. And this, if you studied anything like fluid dynamics in your life, you will identify as the Navier-Stokes equation. Where the only thing remains to notice is that obviously this here is the viscosity. Yeah, and so from measuring viscosity, as I said in the beginning, from measuring viscosity, we can determine the mean free time, and because we know the speed of sound, we can determine the mean free path. And this is actually the way, for the first time in humankind, that somebody could tell how big atoms, I mean, not really how big atoms are, but how far they are apart. Yeah, by measuring viscosity, measuring speed of sound, plugging this into the Navier-Stokes equation, seeing that this is related to the Boltzmann equation, and now knowing this distance. Okay, how many? 7-8 minutes over time. I'm going to stop the recording.